Okay, Foundations of Math 11, here we go. We got video 8. This is our last video in our statistics section, and we were talking confidence intervals. So what's a confidence interval? Where a confidence interval is the specific interval estimate we can make on an entire population using information we've gained from a sample. Because remember, if you survey a sample, you want to be able to extrapolate that data into a population, but you can't always be 100% confident. Because if you were taking a sample of Canadians and you ended up with a result of 1 in 5 as your data, you can't extrapolate 1 in 5 Canadians in your entire population without a minor or less than minor amount of potential error, because that's still a broad generalization. If you only asked 10,000 people in the country as your sample size, the population is way larger than that. So you need to always have a confidence interval. And that tells people things like, oh, within 3%, it's 80%, right? Something like that. So you could be as high as 83 or down to 77, but you want to be able to calculate a confidence interval. Now, what you see here is a graph that represents exactly that. Now, what you have represented by the curve is the standard normal distribution of your sample, and can we determine how much that distribution is underneath our curve with these e-values mean our maximum potential error, right? So what that gives us is it gives us two little tips on the end that we include as what is our confidence error. This is where we give ourselves a margin for error. Now you can see that the room underneath the curve is 1 minus alpha. And what alpha represents is a given percentage to subtract from our probability. So if we wanted a 95% confidence, right? If we had 95% in here, that's 1 minus 5. So in this case, alpha would be 5. Well, that means that that's 5%, that's 5%, and the tails get split in half. So we have 2.5% error and 2.5% error. So however much you have left over from your confidence interval, that is what the tails would represent. So let's say our alpha, or let's go from confidence first. I'll show you another example. That was 95%. Imagine we just had a 90% confidence interval. Well, that means in that case, that's 1 minus 10, right? Because 90% is 0.9. So that would give us an alpha of 10, which would give us here 10 over 2 would give us a 5%, and 10 over 2 would give us a 5% wing of potential error, and we're going to use that in our z-score to determine a value to help us in this lovely, meaty, juicy equation over here. Now in this equation that we'll use, we are given x bar, which is the sample mean, because remember we are starting with a sample in this case. And then we are going to find a standard deviation related z-score probability. We have the standard deviation and we have a sample size. That's what n is. Okay, n is the sample size, and then we're going to have a standard deviation. So let's actually just put this into practice and see how it works. So given a random sample of 64 people, so let's just kind of start to write down the information that we have. Okay, we have a random sample, so n is 64. We have a mean, so x bar is 160, because that's the mean of our sample. And we have a standard deviation of 15. Now, what we need to find, because our equation is this, x bar minus the 1 wing of error, standard deviation divided by root n, is less than the true population mean, and then it's the same thing represented, but this time plus. Now what we need to find, because we're given a good chunk of this information, is we need to find this. We get this from our Z table, because in this case what we're looking for, if it's 95%, it means our alpha value is 5%, so it means that each tail is 2.5%, which means 0.025. So that is the probability region. So we aren't using the Z table looking for 0.25 down the Z column, if you remember using the Z table. We're actually looking in the Z table. So we're finding that kind of inverse Z value of 0.025. And you find that under the Z column of 1.9 and then across the row to 6. So that's going to be that value. So once we found that, and we did that in class, you can see how to use the Z table on the normal distribution video that was before this, just to get a refresher there. But that's the number you look for there. And now it essentially becomes color by numbers. We have X bar, so we're going to plug that in, 160. We've now solved for this value here as 1.96. We know that our standard deviation is 15, so times 15, and then divided by the square root of our n, our sample size, which is 64. And that is going to be less than our true population mean, and then we almost have the exact same, except it's now plus on this side, but it's still 1.96, and then it's still 15, and then over root 64. Now, root 64 is 8, but calculate this all out, right? We're plugging this into our calculator. Please don't forget BEDMAS. Do this multiplication first, and then divide it by root 64, which is 8, and then you end up with 160 minus 3.675 is less than mu, which is less than 160 plus 3.675. So what we get, this is our margin for error. And what we can say is we can say that our true population is between, if you do this last bit of subtraction, you get 156.325. So you can say, well, our true population lies between 156.325 and 163.675. But that doesn't sound as nice as they want it to sound, because what we can actually say is if this was our sample mean, well, that's going to be our population mean. And we're going to say that our population mean is 160. And then you can say this however you want, within 3.675. You could say plus or minus 3.675. And then you say the nice part, 19 times out of 20. Because 19 divided by 20 is 95%. So 95% of the time, our data is going to come out that our population is within 3.675 of either side, which means this number here and this number here of 160. So the population mean is basically the sample mean with a 3.675 margin for error on either side. That is our 95% confidence interval. So a lot of moving parts here, a lot going on. I totally get it. So I think it'd probably be helpful to look at one more example. Now, this example, we actually have some tangible data to look at with this, okay? So a logging company bids on a tract of land to harvest, not old growth forest, that's right, and a random sample of trees. Okay, so there's my first piece of data. X bar is 150. Yields a mean diameter, okay, so mean, or sorry, whoops, not X bar, N is 150, a mean diameter, so X bar of 48 centimeters, and a standard deviation of 5.6 centimeters. But now here we're looking for a 90% confidence interval. So if it's 1 minus alpha is 90%, that means that alpha is going to be 10%. Which means that our Z values of alpha over 2 are going to be 0.05. So what you're looking for on your table is you're looking for Z of 0.05. And what do we get from that? So from that on our table, we get a Z value of 1.64. So now we have all the information we need to plug into our equation. Okay, we have X bar minus our Z half tail times our standard deviation divided by the square root of our sample size is less than our true population, which is less than the same setup but plus. And we can start plugging the values in that we have calculated. So we have 48 minus 1.64 times standard deviation of 5.6, all divided by, in this case, the square root of 150. Now you're going to get good at using your calculator here because we're not always going to get a nice perfect square root like we did last time. So being able to use your calculator properly is going to come in really handy. So again, x bar 48 plus 1.64 and times 5.6. And then again divided by the square root of 150. Now if you calculate all this through, and you calculate it through properly, what you get in this case is you get 47.25 is less than, and then 48.75. So how can we discuss this data? Well, we can say, because we're talking about the mean diameter of the trees that we are harvesting. And in this case, what we can say is our sample gave us a mean of 48. So our true population mean of trees is going to still give us a diameter of 48 centimeters, but in this case, plus or minus 0.75 centimeters, because you can see that is the amount we've added and taken off from here. And then in this case, though, our confidence interval is 90%, so 90 out of 100, which means 9 out of 10. So you would say 9 out of 10 times. So 9 out of every 10 trees you cut down will fall within those parameters based on a 90% confidence interval, right? And that is what the data tells us here, and that's how we can extrapolate that out. So that's confidence intervals. We're really only scratching the surface with respect to how we dive into statistics. It is a very, very, very involved and a very, very, very useful discipline. So if you kind of feel like you like this sort of stuff, consider looking into it in grade 12 offerings where it's found, but then also post-secondary. So statistics are everywhere. We use them to explain things, but not many people understand what they're even reading. So if you like it, keep going. Otherwise, we are moving on to section 3. Thank you so much, and I will see you next time.